Now, we have been working with quadratic equations in the past. We've seen many ways to solve those things. And we will still need that skill to work with quadratic functions. And you'll see where that comes into play here. So, section 3.1, quadratic functions. All right, a quadratic function looks like this, usually. And what qualifies this as being a quadratic function is the fact that we do have a second degree term here. And so therefore we must insist that a never be equal to 0. Because if a is equal to 0, we're not going to have this term. Then this would collapse down to an ordinary linear function. Okay, so this is the term that qualifies this as being a nonlinear function or a quadratic function. All right, now this form here has a name. It is usually referred to as a general form for a quadratic function. And if our leading coefficient a is greater than 0, then the graph of this quadratic function, which is going to always be a parabola, will open upwards. So if the leading coefficient here is positive, then the parabolic graph of this quadratic function will open upwards. It'll look like this. If the leading coefficient a is negative, then the graph or the parabola will open downwards. Now, to locate this graph, we are interested in a very important point called the vertex point of the quadratic function or the parabolic graph. And the vertex point is either going to be the lowest point on the graph or it's going to be the highest point on the graph, whatever the case might be. So if a parabola opens upwards, then the vertex point is going to be, and I'll abbreviate the vertex point as VP. The vertex point will be a minimum point on the graph. It's not only going to be a local or relative minimum, but it's also going to be an absolute minimum. Okay. If the parabola opens downwards, then the vertex point will be a maximum, a relative or local maximum, and also an absolute maximum. How do we find this vertex point? Well, when our function is in general form, we can find the vertex point, and this is derived by using essentially the quadratic formula. We can find the x-coordinate of the vertex point by using this little formula here. The x-coordinate is going to be the opposite of b divided by 2 times a. And then the y-coordinate of the vertex point will be found by taking that x-coordinate value and then evaluating your function at that value. So the y-coordinate is going to be the function f evaluated at negative b over 2a. So that's how we can find the vertex point. Okay. All right, let's look at a specific example. Suppose that we have this quadratic function, f of x is equal to 3x squared plus 12x plus 5. All right, this quadratic function happens to be in general form. And I'm going to ask ourselves several questions regarding this quadratic function here. Okay, so the first thing I'm going to want to do is, let's say, find the vertex point. And to find the vertex point, we can tap into our little formula up here. Okay. All right, so therefore the x-coordinate of our vertex point is going to be the opposite of the linear coefficient divided by 2 times the leading coefficient. So in this case, our b is 12 and our a is 3 and our c is 5. Okay, so we have the opposite of 12 divided by 2 times the leading coefficient 3, which is to say negative 12 over 6 or negative 2. So negative 2 will be your your x-coordinate of your vertex point. Now your y coordinate is going to be found by taking -2 and evaluating the quadratic function at -2. So that's to say we replace x with -2 everywhere. This is going to be 4, so we're going to have 3 times 4 minus 24 plus 5. And this is going to be 12 minus 24 is -12 plus 5 is -7. So therefore, our vertex point is going to be the ordered pair -2, -7. Furthermore, notice since A, our leading coefficient, is positive, so A is positive, the graph of this quadratic function is going to be opening upwards. And therefore, the vertex point is going to be rendered as an absolute minimum point. It's going to be the lowest point on the graph here. So it is going to be a minimum. And that would be an absolute minimum of this quadratic function. All right. Okay. So that's the vertex point. Now, to better assist our ability to graph this function, we might want to find like any intercepts that this thing might have. So the next thing we want to do is maybe try to find maybe a y-intercept. And that is accomplished by letting x be 0. So our y-intercept is going to be the function evaluated at 0, which means x is replaced with 0 throughout, which is just going to give us 5. So our y-intercept turns out to be the ordered pair 0, 5. That's the y-intercept. That's where the graph's going to go to the y-axis at. All right, how about any x-intercepts? Does this quadratic function possess any x-intercepts? Well, to find them, we normally set y, but it's not, our dependent variable is not called y, it's called f of x. We set f of x equal to 0. And then when we set f of x equal to 0, we're essentially having to solve, guess what? A quadratic equation. So now we have to solve this quadratic equation to get our 2 x-intercepts, if they even exist. The quickest way to solve a quadratic equation is usually the factoring method, if it works. Sometimes the factoring method does not work, in which case you may have to, use the completing the square or the quadratic formula. 3 times 5 is 15, but I don't think there are factors of 15 that sum up to 12. So I don't think we have any choice, but we're going to have to use the quadratic formula here. So here we go. X is equal to the opposite of b. My b is 12. So the opposite of 12 plus or minus the square root of my discriminant. My discriminant being b squared minus 4 times a times c, all divided by 2 times a. All right. So we have -12 plus or minus the square root of 12 squared is 144. And that's going to be minus 60, I believe, all over 6. All right, so 144 minus 60, that's us on a good morning, 84. So x is equal to -12 plus or minus the square root of 84. And that's all divided by 6. All right, so our x-intercepts are messy. That's kind of obvious. And can we maybe simplify, the square root of 84? Well, 84 simplifies down into 4 times 21. And the 4, when you take its square root, comes out as a 2. So we got -12 plus or minus 2 times the square root of 21 all over 6. And these are your messy x-intercepts. So one x-intercept is going to be -12 plus 2 squared root of 21 all divided by 6. And another x-intercept is going to be negative 12 minus 2 square root of 21, all divided by 6. So we have two real irrational solutions to this quadratic equation. And so we're going to have two real irrational x-intercepts. And let's see if we can approximate these, see what they are. So we've got negative 12 plus 2 times the square root of 12 divided by 6. So this first one I get approximately about negative 85/100. That's the x-intercept, but that's where the graph will go through the x-axis. And then our other x-intercept is going to be the minus version over here. Divided by 6 here. And I get about negative 3.15 approximately here. So those are your x-intercepts. Okay.
I didn't get the same answer for the first one.
Let me double check that. Maybe I forgot. You know what? Maybe I forgot the 2 in front of the square root of 12 here. Hold on a second here. Huh. Negative 12 plus 2 times. Wow. Maybe I'm turning over a new leaf. I typed in the square root of 12. It should be the square root of 21. Maybe, hopefully I'm not dyslexic. Yeah, negative 0.47. So negative 0.47 there. So that's one x-intercept, and the other one is about negative 3.15. Anybody getting that? 0. So we got two x-intercepts here. Okay. All right, now all parabolas that open upwards or downwards or right or left possess what's called an axis of symmetry. And the axis of symmetry is going to be, in this case, a vertical line that goes right through the vertex point. So the equation of the axis of symmetry is going to be x equal to the x coordinate of our vertex point. And the x coordinate was negative 2. So x equals negative 2 is going to be your axis of symmetry here. That's going to be, again, a vertical line that goes right through the vertex point. It's called your axis of symmetry here. Okay. All right, so let's see if we can sketch the graph of that parabola. And to do so, graphing paper is recommended. And so we plot the vertex point, which is at negative 2, negative 5, negative 2, negative 7, excuse me. So negative 2, negative 7, negative 1, 2, 3, 4, 5, 6, 7. We'll assume these tick marks are spaced 1 unit apart on both axes. So there's the vertex point down there in the third quadrant. The y-intercept we computed was 0.5. So 1, 2, 3, 4, 5. And the x-intercepts, we got 2 of them. One was about negative 0.4, so negative 0.5, about negative 1/2, 0. There's one right there. The other one is negative 3.15, right about there. And this parabola opens upwards. And so wish me luck as I try to put a nice smooth U-shaped curve through these points here, opening upwards here. Okay. There's supposed to be a nice smooth turning point down here, not a sharp V. But we do have a very rather a narrow parabola here. And it's supposed to come up here and then pick up that point and go off like this. Okay, so there you go. And you have your axis of symmetry. And your axis of symmetry is the vertical line x equals negative 2. And that's going to run right through here. That's your axis of symmetry. Okay, so that would be a sketch of the graph of that parabola there. And you could also graph this using your graphing calculator. And using the minimum function, you could identify what this relative and absolute minimum point is, called the vertex point down here. Okay. All right. Any questions about this here, Liz? On how we found all this information about this quadratic function that's written in general form for us. And we ultimately sketched this graph there.
Could you go back to the math for the axis of symmetry?
The axis of symmetry is x equal to the x coordinate. The equation of the axis of symmetry is always x equal to the x coordinate of the vertex point, and the vertex point was -2, -7. So the axis of symmetry is going to be this vertical line, x equals -2. That's the axis of symmetry.
Thank you.
All right, any other questions here? How we analyze this quadratic function, finding valuable information in order to enable us to graph it? Okay, now another form for a quadratic function is this form here. Instead of general form, it is usually to our advantage, and it is our great hope that our quadratic function take on this alternative form here. When a quadratic is written in this form here, it's said to be in what's called vertex point form. It's in vertex point form because we can literally read off the vertex point from the equation. Unlike the general form, we have to actually use that formula there to compute the coordinates of the vertex point. But when the quadratic function is written in this form, the vertex is going to be the ordered pair HK. H is the x coordinate, K is the y coordinate of the vertex point. That's why we call this vertex point form. And this number A is the same number A as it was in the general form. All right, how do we go from general form like this to standard form? How do we go from this form to this form here? Well, that entails a process known as completing the square. And I am going to demonstrate on this quadratic function how we complete the square on it to hammer it from general form into standard form, or into vertex point form, as this is often referred to. So let's go ahead and do that. So let's go back, and here's our original function. Now it's going to be my job to complete the square on this to go from general to vertex point form. And in order to accomplish this, what I'm going to do is, first of all, I have to force a 1 in front of x squared here in order to complete the square on this binomial. To do that, I'm not going to divide both sides of my equation because it's not really an equation. It's actually a function in this setting here. So I'm going to factor a 3 out of both the first two terms here. So I factor a 3 out of the first two terms, and this is what I leave behind here. Fair enough? Still the same function? All right, now we're going to complete the square on this binomial here. And to do that, we're going to have to add the square of half the linear coefficient to it. So that is to say that I'm going to have to add to this binomial half of the square of half of this 4 here. So 4 divided by 2, and we're going to have to square that. But ladies and gentlemen, if I add this number to my function to compensate so I don't change my function, which is illegal, I must turn right around and subtract it right back off. So the net effect is that I've done absolutely nothing, no changes whatsoever to my function. This is still equivalent to my original function up here. Still equal. All right, so further simplifying here. Now 4 divided by 2 is 2, and 2 squared is 4. So it's going to be 4, and then we got the -4 here. Again, doesn't look like it, but this is still equivalent to my original function up here. All right, I created a very special. What's that?
Wouldn't those 4s be 2s?
4 divided by 2 is 2, but then I square the 2.
Oh,
So I got 4. Okay. Now, I created a very special type of trinomial here. This is called a perfect square trinomial. And that always is the end result of completing the square on a binomial. So therefore, it can be factored. So this x squared plus 4x plus 4 can factor into x plus 2 times x plus 2. Or x plus 2 squared. Correct? All right. Now I'm going to take this 3 and distribute it inside the parentheses here. So I'm going to have 3 times quantity x plus 2 squared. And 3 times -4 is -12. We're almost there. We have f of x is equal to 3 times x plus 2 quantity squared -7. And ladies and gentlemen, we have accomplished our task. This happens to be in what is called vertex point form. That's vertex point form now. So we can read off the vertex point immediately. So the vertex point is going to be the ordered pair HK. Notice the minus sign is always part of the vertex point form. And since we have a plus sign here, another way to think about x plus 2 is really to say it's x minus a negative 2. So the x coordinate of my vertex point is not a positive 2. It actually is, in this case, a negative 2. The y coordinate is negative 7. And there we go. We got the same vertex point that we got from our general form when we use that formula. Right? There's your vertex point. I always like to think of it this way. The x coordinate of my vertex point is always the opposite of what this sign is. So if this is a plus sign, the x coordinate is negative. If this is a minus sign, the x coordinate is positive. Any questions how we completed the square on that general form to hammer it into vertex point form? Alrighty. Okay. All right, now, as far as the x-intercepts are concerned for a quadratic function, there is going to be a couple of different possible cases that that occur. And in fact, there's going to be 3 possible scenarios as far as x-intercepts. So in general, what are the 3 possible scenarios for x-intercepts for a quadratic function? Well, one possibility is this. If, ladies and gentlemen, the discriminant of this quadratic function, which is b squared minus 4ac, of course, the quantity underneath the square root of the quadratic formula, if the discriminant is equal to 0, then this would imply that we're going to have only one x-intercept. Can anybody envision or indicate to us what a parabola would have to look like if it only has one x-intercept? Is that possible? For the parabolas that open upwards or downwards, of course. What would that look like? What kind of a parabola would possess one x-intercept if it's the type that opens upwards or downwards? Well, to possess just one x-intercept, if a parabola opens upwards or downwards, it means that the only x-intercept would have to be the vertex point itself. So the parabola can either open upwards looking like this, or it could open downwards looking like this. That would have to be the scenario in that case. One x-intercept. Second possibility, if my discriminant b squared minus 4ac is greater than 0, then we're going to have, in this case, 2 x-intercepts. There will be 2. And in this scenario here, our quadratic function's vertex could either be above the x-axis and the parabola open downwards. That would give us 2 x-intercepts. Or the vertex point could be below the x-axis and the parabola open upwards. And that would also give us 2 x-intercepts. So either one of those scenarios there. But there's one other case, ladies and gentlemen. And what do you think that other case is? What if our vertex, discriminant is not equal to 0? It's not greater than 0, but it might be what? What if it's less than 0? Well, what happens in this case? Well, think about it. This is the quantity underneath the square root. And if it's negative, what's the square root of a negative number? It's no longer real. It's non-real. You got I involved now, the pure imaginary unit. So in this case, there would be no x-intercepts for the quadratic function. What would a parabola look like if it doesn't have any x-intercepts? Well, that means it cannot go through the x-axis or even touch the x-axis anywhere. So that would occur if your vertex point of your parabola is above the x-axis and the parabola opens upwards. There would be no x-intercept. Or your vertex point could be below the x-axis and your parabola open downwards, in which case there would also be no x-intercept. So you got 1 of 3 possible scenarios for x-intercepts for a quadratic function whose graph opens upwards or downwards. Either it has 1 x-intercept, the vertex point itself, 2 x-intercepts, or no x-intercepts. It's got to be one or the other. So your discriminant can give you an idea as to what, how many x-intercepts the quadratic functions graph will possess. All right, I want to go to our textbook here, technology allowing here, and on page, well, this is section 3.1. So I want to look at maybe a problem or two here. So I'm going to go to page 297, number 55. As always, please do spend some time to look at the examples in this book. I think it is very valuable to invest your time in that. All right, number 55 here. Yes, quadratic functions can be applied to the real world. And because the vertex point's either a minimum or a maximum point, they are ideally suited for minimizing or maximizing various functions. For instance, in the business world, we like to maximize revenue or profit, and we like to minimize cost. Well, for that reason, profit and revenue functions and cost functions are often modeled according to quadratic relationships, okay, or quadratic functions. So let's look at number 4055. It says a trough at the end of a gutter spout is meant to direct water away from the house. The homeowner makes the trough from a rectangular piece of aluminum that is 20 inches long and 12 inches wide. He makes a fold along the two lines, long sides, a distance of X inches from the edge. A, write a function to represent the volume that this gutter can basically contain or deal with. And B, what value of X will maximize the volume of water that can be carried by the gutter. And C, what is the maximum volume that can be handled by the gutter here. Okay, so first of all, do we understand that picture there? They have a piece of aluminum 20 inches long, and they fold it in X inches from each end, and then fold up along those lines to form this this canal, if you will, or this gutter that can channel water away from the house. Notice this dimension here is 12 minus X. Why? Because they tell us the entire piece of aluminum was 12 inches wide. But if you take X inches away for this height and X inches away for this height, that leaves you with 12 minus 2X inches left for the remaining width here. So do we understand this picture here? Does that make sense? So as I went for number 55, how do we compute the volume of essentially a box? The volume of a box is computed by taking the length times the width times the height. And so we can develop a volume function here. And this volume function is going to be a function of X alone, because my length is going to be 20 inches times the width. The width is 12 minus 2X inches times the height, which is X inches.
Can we see your screen?
So there you go. So that would be the volume of that gutter, length times width times height. This is the length, this is the remaining width, and this is the height of the gutter. Does that make sense there so far? That's a volume function now. All right, so what we're going to do is we're going to distribute 20x actually into the parentheses here. And so our volume function is going to be, now we have 20x times 12 is going to give us 240x. Minus 2x times x is 2x squared times 20 is going to be minus 40x squared. And we now have a quadratic function, which is our volume function. So putting this in descending order, we have a quadratic function now that represents the volume that this gutter can handle here. Notice our quadratic function is in general form, and our a here, the leading coefficient being negative 40, suggests that our parabolic graph will open downwards. And that kind of makes sense why it would open downwards, ladies and gentlemen, because the vertex point is not going to be a minimum point, but it's going to be a maximum point. And so the answer to this question, as far as the maximum volume that can be, fathomed by this canal or channel, will be held in the vertex point, because that is a maximum point. All right, so in order to do question A now, question A says write a function that represents the volume in terms of X. This is the answer to question A. Question B is what value of X will maximize the volume of water that can be carried away by the gutter. The answer is going to lie in the vertex point. So we need to find the vertex point. Since our quadratic function's in general form, the X coordinate of the vertex point can easily be found by using this formula here, negative B over 2A. My B is the linear coefficient, which is 240. So I have the opposite of 240 divided by 2 times the leading coefficient of negative 40. This will be the X coordinate of my vertex point. And so it's going to be negative 240 divided by negative 80, which gives me 3. So 3 inches would be the dimension of X. That's going to enable us to have a maximum volume of water carried away by this channel. X must have a dimension of 3 inches on that gutter. So we must cut in 3 inches from each edge to maximize the volume that or capacity for this gutter here. So that answers the question for B. X must be 3 inches. And now for C, they want us to compute, okay, well, what actually will be the maximum volume that this gutter can, carry away? Well, when X is 3 inches, we will put this back into our volume function here and crank out the maximum volume. So we evaluate our volume function at 3 inches. And this will give us in cubic inches the maximum volume of water that can be carried away by this gutter when we allow X to be 3 inches in designing this gutter. And the maximum volume is 360 cubic inches. That is the maximum volume. We're done with that problem. So that would be the maximum volume of water that this gutter can transport away from the house, provided that we make cuts of 3 inches in from each edge of the gutter. You cannot do better than this for that gutter. This is the optimal volume, maximum volume that the gutter can deal with based on the dimensions of the aluminum that we were afforded. Okay. And we could have, found this answer graphically by graphing this quadratic function in our TI-84 and then finding the maximum point, which would be the vertex point. And the vertex point would be 3, 360. The maximum volume, 360 cubic inches, would be realized when X is equal to 3 inches. That problem make any sense there? All right, that was number 55. Let's take a look at another one.
Sorry, I'm confused. How'd you get 360?
Well, negative 40 times 9 is going to be negative, let me see. 9 plus 240 times 3, 360. Yeah, this does work out to be 360. I did that again there. So negative 40 times 9 plus, this is going to be 720, correct? Yeah, negative 360 plus 720 is 360. Does that work out? 360 cubic inches. Any other questions about that one? All right, let's take a look here. 53. Number 53s. Hold on a second. I gotta make sure we're adhering to the clock here. All right, number 53. Suppose a family wants to fence in an area of the yard for a vegetable garden to keep out deer. One side is already fenced from the neighbor's property. If the family has enough money to buy 160 feet of fencing, what dimensions would produce the maximum area? So if we have 160 feet of fence to work with, what rectangular enclosure, because there's many different rectangular enclosures you could fathom here, which one would afford you the maximum enclosed area for the garden? So instead of doing a whole bunch of trial and error here, ladies and gentlemen, math can be very helpful. Okay. So we can build an area function involving our rectangular enclosure here. And we know the width of this enclosure is going to be X feet here and here, and the length will be Y feet. And of course, this one, this side, we don't have to worry about because it's already, has a fence here. So now we have 160 feet of fence to work with. And the perimeter of this is going to be equal to the total lengths that we have here. So it's going to be X plus X, which is 2X plus Y. But they tell us the perimeter is 160 feet because that's all the fence we have to work with, 160 feet of fence. So therefore, we develop one equation here that looks like this. That's the total amount of fence we have to work with to build this rectangular enclosure. And we know the area of a rectangle is equal to side times side. So this will be X times Y. Well, ladies and gentlemen, I'm going to take this equation and solve it for the variable Y in terms of X by subtracting 2X from both sides. I get Y is equal to 160 minus 2X. Well, we can substitute 160 minus 2X then in for the Y variable into the area function we're trying to develop. So this can go in for the Y variable. And now my area collapses down into a function only involving X then. It'll be X times 160 minus 2X. Aha, but this area function is a quadratic function. So the area of the enclosed region here is going to be, after distributing the X inside and putting this in descending order, it's going to be negative 2X squared plus 160X. So there's my area function, and it is a quadratic function. Furthermore, the leading coefficient, which is -2, is less than 0. That suggests that the parabolic graph of this quadratic function will open downwards, which makes sense because the vertex point is a maximum point. And I do believe in this word problem, they want us to maximize the enclosed area. So the answer is going to lie in the vertex point. That will be the maximum enclosed area and give us the dimensions that we must build to realize that maximum area. So therefore, the answer lies in a vertex point. So here we go. We got to find the vertex point. So we use our formula to find the X coordinate. It's going to be negative B over 2A. My B is the linear coefficient, which is 160. So this will be negative 160 divided by 2 times the leading coefficient of -2. So this is negative 160 divided by -4, which gives me positive 40. 40 feet. So X has to be 40 feet in order to maximize the enclosed area. Must be 40 feet here and 40 feet here. What would Y have to be? Well, we can put 40 in for X here in this equation and solve for Y. So therefore, Y must be equal to 160 minus 2 times 40, which is 160 minus 80, or 80 feet. So Y would have to be 80 feet. So those would have to be your dimensions of your rectangular enclosure in order to maximize the area. So this would have to be 40 feet here along this edge. This length of fence is 40 feet here, and this will be 80 feet here, and that would add up to 160 feet of fence that we have available to build this enclosure. Now, what would be the maximum area? The maximum area of this fence is going to be found by taking 40 feet and putting it back into your area function, which is a quadratic function. So I'll put 40 in here and put 40 in here for X and crank out the maximum area. And all we have to do is go through the arithmetic here and get this value here. And I'm getting 6,080 square feet. So 6,080 square feet will be the maximum area, the optimal maximum area that you can attain if you have 160 feet of fence to work with. You cannot do better than this. This is the optimal best answer, or the best maximum area, guaranteed by the almighty quadratic function here. Okay. And we're done with that problem. That would be the maximum enclosed area, 6,080 square feet in there. All right, so that's another classic problem involving the use of a quadratic function to help us maximize a quantity, in this case, the enclosed area. So that is number 53 there. Okay. All right, let's see here. Page 297, number 57 here. All right, number 57 here, ladies and gentlemen, I'm going to demonstrate quadratic regression on the TI-84 calculator. I did indicate with an email that there was an example I wanted you to look at to perform linear regression on a bivariate data set or ordered paired data set. This is an ordered paired data set of which I'm going to try to fit these data points with a quadratic or a parabolic curve or a quadratic function. Regression is something that you also study in a course in statistics, Math 150 here at Mott Community College. Okay, you look at regression. It's a method of curve fitting or fitting a function to ordered paired data that you collect out in the field. Tetanus bacillus bacteria are cultured to produce tetanus toxin used in an inactive form for the tetanus vaccine. The amount of toxin produced per batch increases with time and then decreases as the culture becomes unstable. The variable T is the time in hours after the culture has started, and Y of T is the yield of toxin in grams rather. So we have an ordered paired data set. Our X variable, independent variable, is time, and our Y dependent variable is the amount of toxin that we have in grams. So here's what we're going to do. We're going to open up our TI-84 calculator here, and we're going to perform what is called quadratic regression. If I can get my calculator to work properly. All right, so we're going to turn the machine on. We're going to go to stat, S-T-A-T, hit your stat button. Stay on edit and hit enter. And now in list one, I'm going to type in my time values. List one is going to be my X values, which is time. So 8, 16, 24, 32, 40, 48, 56, 64, 72, 80, 88, and 96. So I typed in my time values in list one. Now we go to list two to type in the corresponding amounts in grams. 0.60, 1.12, 1.60, 1.78, 1.90, 2, 1.94, 1.80, 1.48, 1.30, 0.66, and 0.10. So I loaded up list 1 and 2 with the time and Y of T values here. Now we're ready to perform regression. So, ladies and gentlemen, I'm going to get out of this now, this list editing mode here by hitting second mode rather to quit. So second mode quits. And I'm going to show you something really cool here. I'm going to go into my stat plot mode by hitting second Y equals. Second Y equals takes me into stat plot mode. I got 3 stat plots at my disposal. They're all turned off presently. I'm going to go into plot 1 and turn it on. Hit enter to dive into stat plot 1. Toggle it on by hitting enter. Now I'm going to choose the scatter plot icon right here by moving my cursor on it and hitting enter. Notice my X list better say list 1. My Y list better say list 2. If these lists were something different, let's say if my X list was like list 3, how could I force the name L1 into my X list? Well, above your number 1, 2, 3, 4, 5, 6 keys, you see L1, L2, L3, L4, L5, L6. To force in the name of list 1, I would have to move my cursor on the X list up here and hit the second key followed by the number 1 key. That forces in the name of list 1. Everybody see that there? All right, second mode to quit. We have configured plot 1 to give us what's called a scatter plot. And I'm going to take a look at that scatter plot right now. To do that, I'm going to hit my zoom button at the top of my keyboard, zoom. I'm going to go down and select the zoom stat function down here. What the zoom stat function does is it looks behind the scenes at your data very quickly, and it basically scales your X and Y axis appropriately so you can see your scatter plot. So hit enter, select the zoom stat function. And ladies and gentlemen, there's your scatter plot, where the horizontal axis is the time axis and the vertical axis is the yield of this toxin in grams. You can see that the amount of toxin tends to max out and then basically tends to drop off as time progresses. I am going to fit this data with a parabola opening downwards. I'm going to have my calculator develop a quadratic function whose parabolic graph fits these data points the best. That's called the least squares regression curve that we're going to try to come up with. This is called regression analysis to fit this data with a curve. To do that, I will get out of this second mode to quit. I'm now going to go back to stat, but this time go over to calculate. I'm going to go down and grab not my linear regression. I'm not trying to fit a line to this data because that's not appropriate here. We're trying to fit a parabola to this data. So we go down and select not linear regression, but quadratic regression. There's all different types of regression. You got cubic regression that tries to fit a third degree function to your data. Quartic regression tries to fit a fourth degree polynomial to your data. We have natural log regression, logarithmic data tries to fit a logarithmic function to your data. We have trigonometric regression that tries to fit like a sine or cosine wave to your data. We're going to try to fit a parabola to our data by selecting quadratic regression. Hit enter. Notice my X list better be list 1. My Y list contains my Y coordinate data, which is list 2. Go to, leave your frequency list blank. Go down to store regression equation. I'm not only going to have my calculator compute the quadratic regression function that fits this data the best, but I'm also going to have the calculator store it in variable Y1 so that we can see the graph of the quadratic function overlay our scatter plot. So with our cursor sitting in this field to the right of store regression equation, I'm going to hit my vars key right here, VARS. Go over to YVARS, stay on function, hit enter, and select Y1. Enter. Now we go down to calculate. Boom. There, ladies and gentlemen, is your quadratic regression equation that fits this data the best. You cannot do better with any parabola than this one here. This is the optimal parabola that fits these data points the best, minimizes the errors. And this equation is complements of a powerful branch of mathematics called differential calculus. So differential calculus ensures that this is the optimal fit for that data with a parabola. This is the optimal parabolic or quadratic function that fits that data. You could not do better than this right here. All right. So our quadratic function is y equal to negative 8.379 times 10 to the negative fourth x squared plus 0.081198 blah, blah, blah times x plus 0.039 blah, blah, blah as your constant. Now, the beautiful thing about this is, and you don't have to do this, but I'm going to show you by hitting y equals, I'm going to show you that that equation was pasted into y1 in my equation editor because I told it to paste it into y1. Now, ladies and gentlemen, if you just hit your zoom button, go down to zoom stat, not only are you going to see your scatter plot, but you're going to see overlaying this scatter plot the graph of that best fit parabolic graph. And there you go. You could not do better with any other parabola to fit these data points the best. You can see that this parabola fits a lot of these data points perfectly. But in this case, it slightly predicts the amount of toxin. Here, it slightly over-predicts the amount of toxin. Here, it slightly under-predicts the amount of toxin. But you got to admit, that's a pretty tight, good fit here. And like I said, based on the fact that the regression model was developed from differential calculus, I think we can rest assured that this is the optimal fit. You cannot do better than this for a quadratic function. Okay, so that's how you perform quadratic regression on an ordered paired data set. And this is recorded, so if you missed any of this, you'll be able to, go back and digest that. All right, we are done with that section. We have got to move on. The next section now is going to introduce us to what are called polynomial functions. polynomial function. Section 3.2. Intro to polynomial functions. In general, ladies and gentlemen, an nth degree polynomial function looks like this. Where you could have a lot more terms in between here. This is how we, in general, represent an nth degree polynomial function, where these a's are just numbers, or real numbers are the coefficients, and x are the variables, okay? We have an nth degree polynomial function in general. And to be an nth degree polynomial function, we must therefore insist that the leading coefficient not be equal to 0. Otherwise, we're not going to have an nth degree polynomial function. At best, we would have an n-1 degree polynomial function. The domain of polynomial functions, I think I indicated earlier in class, is always the set of all real numbers. Always the case. Always the case for any polynomial function. There's two characteristics, ladies and gentlemen, that all polynomial functions have. Number one, all polynomial functions are smooth functions, or they are smooth graphs, or they have smooth graphs. Number two, all polynomial functions graphs are continuous. So these are two characteristics or traits that all polynomial function graphs exhibit. They're smooth and they're also continuous throughout the domain. So this would be a graph of a function that would qualify as being a polynomial function. It's definitely a smooth graph, and it is continuous throughout the entire domain. This would be an example of a graph of a polynomial function. It's smooth. Notice the turning points up here are smooth turning points. They're not sharp turning points. None of this stuff. Okay, smooth turning points, and it's continuous. Continuous is to say that there's no break in the graph. In other words, you would never have to lift your pen or pencil off this graph ever as you trace its graph in its entirety. You'd never have to lift your pencil or pen off the paper. That means it's continuous. Okay. In Calculus 1, you study continuity of functions. You put it under the microscope. All right. So smooth and continuous are graphs of polynomial functions. So I have a question. Would the graph of this function qualify as being a polynomial function? Yes or no? Is that a polynomial function? This is a polynomial function. Is this one a polynomial function? This is not a polynomial function because it's not smooth. It has very sharp turning points here. These points are called cusp points, okay? All right, not a polynomial function. Polynomial function, not a polynomial function. All right, is this graph a polynomial function here? Is this a polynomial function? It certainly seems to be a smooth graph, but why is it not a polynomial function? It's smooth. Why is it not a polynomial function? Well, watch my pen as I trace the graph. I must pick pen up off paper, place it over here, and then continue. Because I had to pick my pen off the paper, ladies and gentlemen, this function is not continuous here. Okay, not continuous. Therefore, it's not a polynomial functions graph. Not continuous, not a polynomial. All right, any questions about that? So do we know what a polynomial functions graph must look like versus does not look like? All right, so to save some time, let's go back to our textbook now. Now this hangs out in section 3.1. Make a note of this here. I'm sorry, in 3.2, introduction to polynomial functions here. Ladies and gentlemen, we're going to warm up to this notation here because it's going to become very important when we look at the next theorem, okay? If you see X with a little arrow pointing to positive infinity, we read this notation as this way. We say as X approaches infinity. That's how you read this notation. X approaches positive infinity. Approaches positive infinity. Okay. This notation here is to be read as X approaches negative infinity. And you see this notation in calculus 1 when you start looking at the limit of a function. This notation is read as f of x approaches positive infinity. This is read as f of x approaches negative infinity. Now, f of x is the y coordinate. Okay, x is, of course, the x coordinate. All right. So this is saying as x becomes very large, or as x becomes very small, or as y becomes very large, or as y becomes very small. Do you understand that notation there? All right, now this theorem I would memorize. It's called the leading term test theorem. This theorem can indicate to us the leftmost and rightmost behavior of the graph of a polynomial function, just based on its degree and the nature of its leading coefficient. For instance, if I have an nth degree polynomial where my leading coefficient is a sub n, then, les amis, we say that if n is an even number, in other words, if I have an even degree polynomial, like a second degree or a fourth degree or a sixth degree polynomial, etc., and my leading coefficient is positive, so if I have an even degree polynomial with a leading coefficient that's positive, then we would expect the leftmost behavior of the graph of this even degree polynomial to be going upwards forever, and the rightmost behavior of the graph of this such a polynomial would also be going up forever. Symbolically, technically, that's to say as x approaches negative infinity, as we go far to the left on the x-axis, f of x will be going upwards towards positive infinity. And that's to say as we go far to the right on the x-axis, as x approaches positive infinity, f of x will also be moving upwards towards positive infinity. If we have an even degree polynomial with a leading coefficient that's negative, in other words, if this a sub n out front is a negative number, then the left and rightmost behavior of the graph of such a polynomial will be having the graph going downwards, both to the left and to the right. Technically, that's saying as x approaches negative infinity, f of x dives down towards negative infinity. As x approaches positive infinity, f of x dives down towards negative infinity. If, on the other hand, we have an odd degree polynomial, like a third degree or fifth degree or seventh degree, etc., polynomial with a leading coefficient that's positive, then the left behavior of the graph of such a polynomial will have the graph going downwards, and the right behavior will have the graph going upwards. Technically, as x approaches negative infinity, f of x dives down to negative infinity. As x approaches positive infinity, we go far to the right on the x-axis. F of x is blowing up to positive infinity. If we have an odd degree polynomial with a leading coefficient that's negative, the left and right behavior basically flip-flop. The left behavior has the graph going up forever, and the right behavior has the graph going down forever. I would memorize this theorem. It will facilitate our ability to sketch the graph of a polynomial function. So this is a very important theorem. That is on page 302 in your textbook. The leading term test theorem. All right, make sure you know that one. All right, so let's put that theorem to work here for us. So if I give ourselves this polynomial, it happens to be a fifth degree polynomial function, what would be its left and right end behavior? Well, notice this is an odd degree polynomial with a leading coefficient that is negative. And so from that theorem that we just looked at, what would be the left behavior of this graph? Does the graph go upwards or downwards for an odd degree polynomial with a negative leading coefficient? See, your leading coefficient is negative, and your degree is what? An odd degree. Okay. So what would be the left behavior of this graph here? Well, if you go back to that theorem, you can see that for an odd degree polynomial with a leading coefficient that's negative, the left behavior will have the graph going upwards towards positive infinity, and the right behavior will have the graph going down towards negative infinity. So the left behavior has the graph going upwards, or to be more technical, we would say as x approaches negative infinity, f of x will be approaching positive infinity. The right behavior of this odd degree polynomial function would have the graph going downwards forever. And therefore, we say as x approaches positive infinity, f of x is approaching negative infinity. That's the right behavior. Anybody see that there? All right. And you could confirm this later on, but if you just graph this on your graphing calculator here, you could definitely convince yourself that this is all playing out the way the theorem predicts. So if you throw this in your graphing calculator here. And oh, by the way, when you graph functions, make sure your stat plots are all turned off. Plot 1, 2, and 3 better not have anything like this showing. This is indicating that plot 3, your stat plot 3 is turned on, and you'll have a scaling conflict when you try to graph some sort of a function along with this plot, stat plot. So just make sure that your stat plots are all turned off. To turn them off, you just move your cursor up to the plot name, hit enter, and it toggles it off. If you want to turn it on, you can do the reverse. All right, so anyways, I want to graph negative 4 x to the 5th power plus 6x to the 4th plus 2x. And we're going to take a look at this graph and see if the left and the right behavior of the graph is in line with the prediction from this theorem here. And you can definitely see that that's the case. So the left behavior has the graph going up, the rightmost behavior of the graph is going down. So that makes sense. Correct? According to the theorem. All right. Let's try this one here. G of x is equal to 1/4 times x times 2x minus 3 cubed times x plus 4 squared. All right, what is the degree of this polynomial? And what is the leading coefficient? Well, this one's more difficult to determine, but if you were to take this 2x minus 3 and cube it, you're going to generate a 1/3 degree term. So by cubing this or expanding this out, if you will, we're going to get an x cubed term. Expanding this out, we're going to get an x squared term. And we have an x term here. So what is the degree of this polynomial? X times x cubed times x squared is going to give us an x to the 6th power. So this is going to be a 6th degree polynomial. Everybody clear on that? 6th degree. What would be the leading coefficient? I don't care exactly what it is. I just care whether it's positive or negative leading coefficient. What do you think, ladies and gentlemen? Positive or negative leading coefficient? Well, I got this 1/4 out here, and when I cube this or expand this out, I'm going to have 2x cubed as the maximum term coming out of that one. And this is going to be 1x squared coming out of this one. Well, I think it's safe to say that this is going to be a positive and this is going to be a positive coefficient. And a positive times a positive times a positive means our coefficient is going to be what? Positive. So our leading coefficient will be positive. So I have an even degree polynomial with a leading coefficient that's positive. What would be the left and right behavior of this graph? Well, according to the theorem, even degree, positive leading coefficient, that means both the left and right behavior of the graph will be going upwards. Upwards. And so the left behavior of the graph will be going upwards. That's to say, as x approaches negative infinity, f of x will be approaching positive infinity. The right behavior also will have the graph going upwards. That's to say, as x approaches positive infinity, f of x is also approaching positive infinity. All right. And so therefore, if you were to sketch the graph of this, in general, the left behavior has the graph going upwards and the right behavior has the graph going upwards. Now, I don't know exactly what's going on here as far as the number of turning points are concerned, but I do know the left behavior and the right behavior has to be this, guaranteed. We will try to shed light on what's going on in between here, okay, a little later on. All right, does that make sense, that theorem there, what it can tell us? It can tell us the left and rightmost behavior of a polynomial function in the graph there. All right. Okay, suppose that we have a polynomial function, y equals f of x. We say the values, or the value or the values, x, that are in the domain of this function, that's the domain, such that our function evaluated at x is equal to 0. If that's the case, so if we have some value x that we throw into our polynomial function and it gives us a value of 0, then we call these values of x zeros. So they are literally called zeros, or sometimes referred to as roots of f of x. Okay. They are called zeros or roots, zeros, because they send our polynomial function to a value of 0. That's why they're called zeros. It's a well-known fact that zeros are also called roots, but they're also called something else. They're also called x-intercepts of f of x. So zeros, roots, x-intercepts of f of x mean the same numbers. All right. They are all synonymous names for the same numbers here. All right, let's dive right in. Let's try to find the zeros. And we are going to, in this chapter, we're going to introduce ourselves to some very powerful theorems that enable us to find zeros of higher degree polynomials, and also enable us to do something that we could never even think of doing back in elementary or intermediate algebra, and that is taking a huge polynomial and completely factoring it into linear factors, something that we were not even equipped to do back in those earlier courses. So suppose you want to find all the zeros of this third degree polynomial function, f of x equals x cubed plus x squared minus 9x minus 9. And suppose that we then want to maybe sketch the graph. Okay, so we're going to try to do a couple things with this third degree polynomial here. All right, so how do we find the zeros? To find zeros, ladies and gentlemen, which are really known as x-intercepts, we always set y, or in this case, we set f of x equal to 0. Because that's how we find those values called x that cause our function to go to a value of 0. They're called zeros. So we said f of x equal to 0, which means we're really going to have to solve this third degree polynomial equation. And how do we solve this? Well, up until now, the only thing we really have in our arsenal, based on the earlier courses we've hopefully been through, is our ability to maybe factor this left side completely. So we try to tap into our factoring skills. Now, notice, unfortunately, we cannot factor anything out of all 4 terms. So because it's a 4-termer, the next thing, or the next great hope, is the grouping method. Maybe, or hopefully, this polynomial can be factored via grouping. So we will try to factor it via grouping. Careful how you group your last 2 terms together. Leaving the minus sign outside the parentheses means you must adjust the sign of last term to a positive to avoid a sign mistake. What can I factor out of the first 2 terms? I can factor out an x squared, leaving behind x plus 1. Last 2 terms, I can pull out a 9, leaving behind x plus 1. Now we can factor this common binomial factor of x plus 1 out of both terms. And when we do that, in the wake of that, we leave behind x squared minus 9. But ladies and gentlemen, we're not done, because this is the difference between perfect squares. It itself can be further factored down into conjugate binomials. Now we set all of our factors equal to 0 and then solve all the resultant equations to crank out our 3 zeros, or 3 roots, or 3 x-intercepts for this third degree polynomial function. So one 0 is -1, another 0 is -3, another 0 is +3. These are all the zeros. These are all the zeros, or they're also called the X what? They're called the X-intercepts, same thing. Or they're called the roots. They all mean the same thing, all right? So now we know all the X-intercepts, coupled with the fact that we know that leading term test theorem, we can maybe predict what the graph of this is going to look like. Without using a graphing calculator, we can probably begin to sketch this graph, armed with all this knowledge. Any questions how I found all the zeros there? Is it just a coincidence that we have 3 zeros for a third-degree polynomial function? The answer is no. We're going to run into a very powerful theorem called the fundamental theorem of algebra in this chapter 3, ladies and gentlemen. And that theorem basically guarantees that when you have an nth degree polynomial function, you're always going to get n zeros. Now, that is not guaranteeing that all your zeros are going to be real. Some could be imaginary or complex. But in this case, it turns out all of our zeros are real zeros, right? So it's not just a coincidence that we got 3 of them. All right, so let's see if we can begin to sketch the graph of this thing here. All right, and we're going to take a look at this this graph. Okay. Now, before I graph this polynomial function, ladies and gentlemen, I notice I got it completely factored out here on the left side here. And notice that all these factors are raised to the 1 power. So they're all raised to an odd power, these factors. There's significance in that. And the significance of that hangs out in another theorem in this section. It's called the touch or cross point theorem. And I'm going to go over that theorem now and come back to this, and I will graph this, all right? I'm not going to abandon this. I'm going to come back and eventually sketch the graph of this. But I think now would be a good time to look at a very important theorem, which is called the touch or cross point theorem. Touch or cross point theorem. And all theorems are valid, proven statements in mathematics. Now, this is not a proof writing class, but all these theorems do have a proof to them, okay? And they have been scrutinized through the annals of time by brilliant minds. And I would like to think my mind is one of those, but let's be honest, I just stand on the shoulders of giants just trying to convey this information. If C, ladies and gentlemen, is a 0 of f of x, we'll assume that some real number C is a 0 of f of x. In other words, what does that mean then? That means that if I evaluate this polynomial function at C, I better get what? What do you think this has to give me if C is a 0? What must this be equal to? If C is a 0, then f of C must be equal to, you got it, 0. Has to be the case. Okay. Now, suppose this 0C results from a factor of f of x in the form of x minus c. And this factor is raised to the nth power. So suppose this 0C comes from this factor that's raised to the nth power. All right, this theorem says this, ladies and gentlemen. Then the graph of f of x will cross, it will actually cross the x-axis at x equals c if n is odd. So if this factor is raised to an odd power that yielded this 0C, then the graph of f of x will cross the x-axis at c, guaranteed. It'll go right through the x-axis at this value. However, the graph of f of x will just touch the x-axis. But not cross. It will just touch the x-axis, but not cross the x-axis at x equals c if n is even. That's the touch cross point theorem. So, ladies and gentlemen, if the factor that gave us this 0c is raised to an even power, then the graph of f of x will not cross the x-axis at c, but will just touch the x-axis at c and then bounce back. Very important theorem, because this really enables us to sketch the graph of a polynomial function in between its left and rightmost behaviors. So this is a critical little theorem here called the touch cross point theorem. I would memorize this theorem. So let's go back and see if we can apply this touch cross point theorem coupled with the leading term test theorem to accurately sketch the graph of this third degree polynomial function that I worked so feverishly in actually identifying the x-intercepts or the zeros for. I think we have more than enough information to accurately sketch the graph of this third degree polynomial function. It will be a sketch though, keep in mind. It's not going to be 100% precise. I'll show you why. I'm going to take a piece of graphing paper here. And ladies and gentlemen, I'm going to begin to sketch the graph of this third degree polynomial function. Now remember, the x-intercepts are what? -1, -3, and 3. So I have a question for you. Is my graph going to cross through the x-axis at -3 or actually just touch the x-axis at -3? Well, -3 came from this factor here, x plus 3 equal to 0. And that factor was raised to the first power, which is an odd power. Because x plus 3 is raised to an odd power, we would say the graph is going to actually cross through the x-axis at -3 by the theorem that I just mentioned, the touch cross point theorem. So the graph will actually cross through the x-axis here. Crosses right through it. And x equals -1, which came from this factor x plus 1 being set equal to 0, and x plus 1 noting was also to an odd power. My graph will also cross through the x-axis at -1, guaranteed by that theorem. 3, another 0, came from the factor x minus 3 being set equal to 0, and x minus 3 noting it was to an odd power. Our graph will also cross the x-axis at 3, guaranteed by the cross touch point theorem. So my graph is actually going to cross through the x-axis at these 3 x-intercepts. That's valuable information. All right, so let's go here. Let's plot -3, -1, 2, 3. We'll assume our tick marks are spaced 1 unit apart on both axes here. So my graph has to cross through the x-axis at -3. But ladies and gentlemen, what's the left behavior of this graph? What is the left behavior of this odd degree polynomial with a leading coefficient that's positive, +1? Will the graph be going upwards or downwards for an odd degree polynomial with a positive leading coefficient? Use that nth term leading test theorem, and you can discover, hopefully, that for an odd degree polynomial, leading coefficients positive. What did that theorem say? It says the left behavior of this graph is going to be what? Going down or up? What was the case? Down or up? What was that? Down, down, down. The right behavior of this odd degree polynomial with a positive leading coefficient, I believe, had the graph going upwards, correct? So therefore, knowing my leftmost x-intercept is -3, and knowing that my graph has to cross through the x-axis at -3, and knowing that the graph left behavior has to be downwards, my graph has to start this way. So ladies and gentlemen, starting from the left, I have to come through this point. Have to. I'm starting to sketch my graph here. Okay, got my left behavior, and I'm coming through the point x equals -3. As the theorem predicted, the graph must cross through the x-axis at -3. But my other x-intercept, my next one, is -1. And my graph has to cross through the x-axis at -1. It has no choice based on the theorem. So my graph has got to turn around somewhere in between -1 and -3. The graph has got to turn around and come back down through the x-axis at -1. Now, here's the uncertainty of the graph. Where does it turn around? Does my graph turn around here, or does it go up real high up here and then turn around and then come back down through -1? Exactly where does it turn around in here between -1 and 3? We don't know the answer to that question, ladies and gentlemen. But to answer that question, after you get done with calculus 1, you'll know precisely where this graph turns around in between -1 and 3. When you are introduced to something called the derivative of a function, differential calculus. Okay, but we don't know that yet. So we don't know exactly where this turns around in here between -1 and -3. It could turn around real low down in here, or it could turn around way up here. We don't know that. So I'm not going to expect you to know exactly where that turns around. So we'll just have it turn around somewhere in here. Don't worry about it, just have it turn around somewhere. And it's got to come through the x-axis at -3, at -1, excuse me. So it's going to cross through the x-axis at -1. Now you could find the y-intercept if you want to. For a little more accurate graph, finding the y-intercept is not that difficult. All you do is let x be 0. So the y-intercept is going to be f of 0, which is going to be what? Putting in 0 here, here, and here, our y-intercept will just be what? -9? Isn't that true? That drops out, that drops out, that drops out. When you put 0 in for x, we got -9. So your y-intercept is -9. That is a certainty. So my graph is going to have to come down here and go through the y-axis at -9. Wow. -1, 2, 3, 4, 5, 6, 7, 8, 9. It's got to come way down here and cross through the y-axis. So I got to be real steep in here, real steep. It's got to come in here. Now my next x-intercept is +3. So my graph is going to have to turn around somewhere in between -1 and 3. It's got to turn around somewhere in here because it's got to come back through the x-axis. It has no choice based on the theorem. So it's got to turn around. Now, where it turns around down here, I don't know. Maybe it goes down further and then turns around, or maybe it turns around right away after it goes to the y-intercept. I don't know. I'm just going to turn it around here somewhere. Doesn't matter exactly where you turn it around. It's got to come through the x-axis at -3. It has to. And the rightmost behavior also predicts the graph must be going upwards. And this is making sense. Ladies and gentlemen, we have the sketch of the graph, and that's a pretty accurate sketch based on all the theorems we learned and everything we know about the polynomial function. Everybody understand how I sketched that graph? Based on all the theorems we learned, the leading term test theorem and the cross touch point theorem. That's a sketch of your graph. Pretty accurate. The only inaccuracy is exactly where this turns around, where this turning point is here, and where this turning point is here. Calculus 1 will answer those questions precisely, very easily. You could find those turning points if you knew calculus 1. Okay. All right. Any questions about that? All right. So we're learning these theorems here, and these theorems are going to help us out, hopefully, in sketching the graphs of these things here. Uh-oh. Where's the clock? 9:24. Oh, he's fighting the clock. And guess who wins? All right. Page 305. Where is page 305? I want to go over like example 4. That's what I have in my notes here. Here, ladies and gentlemen, is the cross touch point theorem. Right here in the purple box that I illustrated on my overhead. It's on page 305 for your viewing. And again, if you miss anything, always try to go through these sections and look at all the examples. I know if I was a student in this class, I would read these sections with a fine-tooth comb. Okay. All right, let's take a look at this one here. This is example 4. We're just going to walk through this example. It's a very, very wise thing to always be looking at these examples and try to study what's going on with them. It says determine the zeros and their multiplicities. Notice it says multiplicities for the given function. You know, for the last problem I did here, we would say that all these zeros here, ladies and gentlemen, have a multiplicity of 1. -1 is a 0 with multiplicity 1. -3 is a 0 with multiplicity of 1. And 3 is a 0 with multiplicity of 1. Okay, these all have a multiplicity of 1. They occur one time, we say. Okay, sometimes zeros have multiple multiplicities. Let's look at this one. Here is a polynomial function, and I have a question for you. What would be the degree of this polynomial function? Anybody? What would be the degree if you were to expand it all out?
5.
That's
3.
right. Well, this if you expand x minus 4 squared out, you're going to get a second degree term in x, aren't you? X squared. If you expand this 2x plus 5 out by raising it to the third power, you're going to get a third degree term. So what's a second degree term multiplied by a third degree term? That would give you, in an overall sense, a fifth degree term. This would be a fifth degree polynomial. And another question is, would its leading coefficient be positive or negative? positive or negative? Well, if you got 1x squared, you're going to have 1 for the leading coefficient. If you got 2x to the third power, you're going to have 8 for its coefficient. 8 times 1 times 1/10 is going to be a positive leading coefficient. And so, ladies and gentlemen, being an odd degree polynomial with a leading coefficient that's positive, we can predict the left and rightmost behavior of the graph of this 5th degree polynomial function. Furthermore, what would be the zeros? If I set this thing equal to 0, ladies and gentlemen, that means I got to set these factors equal to 0, x minus 4 equal to 0, and 2x plus 5 equal to 0. And I would crank out my zeros of being 4, 0, negative 5, half 0. Notice 4 is a 0 of what multiplicity? It's of even multiplicity because this factor is raised to the second power. The other 0, negative 5 halves, which is negative 2.5, would be of odd multiplicity because it came from a factor raised to an odd power. All right, let's put this together coupled with all our theorems and try to reconcile this graph. Notice the left behavior being an odd degree polynomial with a leading coefficient that's positive, the left behavior has the graph going down to negative infinity. The first x-intercept we encounter is negative 2.5. And ladies and gentlemen, since negative 2.5 came from a factor that's raised to an odd multiplicity, the touch cross point theorem predicts that the graph will have to go through the x-axis at negative 5 halves. It actually crosses through. And the graph's y-intercept, if you let x be 0, putting 0 into this function for x throughout, you'll discover the y-intercept looks like about 200. And our next x-intercept is going to be 4. So our graph has to turn around somewhere in between negative 2.5 and 4. The graph has to turn around because it has to come back down and contact this x-intercept. But because our next 0, 4 came from a factor of x minus 4 that's raised to an even power, the touch cross point theorem predicts that the graph will just touch the x-axis at 4, but not actually cross through the x-axis at 4. And that's exactly what the graph does. It comes down and touches the x-axis at its x-intercept of 4, and then it moves back up. Stop and think, ladies and gentlemen, why would the graph have to go back upwards? Why could it not just continue on downwards forever? Because that would defy the what? The leading term test theorem. Because the rightmost behavior of this graph has to be going upwards, being an odd degree polynomial with a positive leading coefficient. So you see how those theorems complement each other and cooperate with each other? That's very important that they do. Otherwise, math is inconsistent. And I've been preaching lies for 20-some years, and I'm going home. Does that make sense, ladies and gentlemen? All the theorems cooperate with each other in mathematics. It's a very beautiful structure in a way when you look at the large picture of things. All right, so all those theorems agree with this graph. Does that make sense? The analysis poured into that graph there and how it cooperates with all the theorems we learned up to this point here. Here's a graph of another one. This is x to the 4th minus 2x squared. Being an even degree polynomial with a positive leading coefficient of 1, the left rightmost behavior theorem says that both branches of the graph will be going up towards positive infinity, up and up. Furthermore, if we try to find the zeros of this polynomial function, notice they factored it. They factored it completely into linear factors. Setting x equal to 0, we get 1 0 as being 0. And notice our x-intercept of 0 comes from a factor x raised to an even power. So the touch cross point theorem says the graph would have to touch the origin at 0 or touch the x-axis at the origin, but not cross through the x-axis at the origin because x is raised to the second power. These other zeros, positive square root of 2 and negative square root of 2, come from factors raised to odd powers, and therefore the touch cross point theorem would predict the graph would actually have to cross through the x-axis at negative square root of 2, which is about negative 1.414, and also pass through the x-axis at positive square root of 2, about 1.414. Is this making sense here? You see how these theorems are basically in agreement with the graphs of these functions? And that's the point of this section here, is to warm up to this idea. Okay. All right. Another thing here, ladies and gentlemen, are turning points. I've been kind of like, throwing that term out loosely here. Turning points are basically where your graph turns around. I have a graph of a polynomial function. Notice it's a smooth continuous graph, as they are always. I have 3 turning points here. I have a turning point here, here, and here. And notice that turning points occur at relative extrema values, correct? I have a relative maximum here, a relative minimum, and a relative maximum here. These are called turning points here. There is a theorem, ladies and gentlemen, yes, another theorem in this section. It's called the turning point theorem. It says that if we have an nth degree polynomial function, then this theorem guarantees that the polynomial function's graph will have at most n minus 1 turning points. This is the theorem. It says that if you have an nth degree polynomial function, the graph will have at most n minus 1 turning points. What does it mean to say at most? Is that saying it will have exactly n minus 1 turning points? It's not saying that. It's saying that the most it could have is n minus 1 turning points, but it could have fewer than n minus 1 turning points. That's what at most means. It means fewer than or exactly n minus 1 turning points. So if I have a 3rd degree polynomial function, f of x equal to x 5x cubed, this graph can have at most 3 minus 1 or 2 turning points. That's all it can have, 2 turning points. And ladies and gentlemen, if you were to take the time to actually graph this function, you would hopefully discover that it does have what? Does it have 2 turning points? If you graph f of x equals 5x cubed? Well, the left behavior being an odd degree polynomial with a positive leading coefficient, the left behavior will be taking the graph downwards, and the right behavior will be taking the graph what? Upwards, correct? And so if you were to throw that graph into your that function in your graphing calculator, would it have at most 2 turning points? Well, we can take a look here and see if that's the case here. At most 2 turning points. Now, this is saying at most 2 turning points. It may have fewer than 2 turning points, but it can have no more than 2 turning points. Let's say I actually zoom in here at the origin. So really zooming into this graph here. And we could maybe, maybe even zoom in even more here. Okay. So we can see the graph does go through the origin, and it would have to go through the 0.00 since x is raised to the 3rd power, an odd power. Do we actually have a turning point here? Well, this graph does not actually, turn around and then dip down and then go to the origin. We would say this 0.00 qualifies as being what's called an inflection point, and that you will discover in Calculus 1 what that's all about. But ladies and gentlemen, the theorem is guaranteeing that the graph of this 3rd degree polynomial function will have at most 2 turning points. It's not saying it's gonna have 2 turning points. It could have fewer than 2 turning points. So in this case, it looks like there would not be any turning point in this graph here, because that's an inflection point. But that's to say that it does not contradict that theorem. Okay, the theorem says it will have at most 2 turning points, meaning it could have fewer than. In this case, it has fewer than. All right. Okay, so that's the turning point theorem there. All right. So let's see where we are with the clock here, 9:35. Okay. All right, so I will give you your classwork. This will probably be the only classwork, as we were having to go through so much material through this section that the clock is against us. So, ladies and gentlemen, for your only classwork today, being the 23rd day of February, I want you to find all the zeros and graph. I want you to find all the zeros and sketch the graph of this polynomial function here. Go ahead and do that problem, find all the zeros, and then I want you to sketch the graph of that function. Remember, it's just a sketch, just do the best you can with the turning points. You don't have to be precise exactly where it's turning around, okay? But go ahead, do that problem. All right, so here we go. To find all the zeros of this polynomial function, you're probably going to have to factor this completely. You're going to set it equal to 0 because that's how we find zeros, is by setting y, which is f of x, equal to 0, because zeros are x-intercepts, correct? That's how we were taught to find them in the past. So we have to completely factor this. I'm using the grouping method, and notice the grouping method does work here. The difference of squares can be further factored down into this. And then remember, this is all set equal to 0. So that means that you're going to now have to set each of these factors equal to what? 0 to find all your x-intercepts or your zeros. And when you do that, you discover that you get 1 is a 0, positive 5 halves, and negative 5 halves are zeros or x-intercepts. And 5 halves is 2.5. And I wrote them this way for graphing purposes. Notice all of these zeros or x-intercepts or roots are of a multiplicity of 1 because they all occur one time, because all their factors are raised to the first power. Because all the factors are raised to an odd power, the touch cross point theorem indicates that the graph will have to cross through the x-axis at each of these x-intercepts. Furthermore, the left and right behavior of this graph, being an odd degree polynomial with the positive leading coefficient, has the left behavior going down and the right behavior going up. Based on all that information, ladies and gentlemen, and I also found the y-intercept by letting x be 0 and discovering the y-intercept when you put 0 into the function is 25. I'm now able to sketch the graph rather accurately for this third degree polynomial. Notice the graph does pass through the aforementioned x-intercepts or zeros, passes through the x-axis, and the left behavior is down, the right behavior is up, and the y-intercept is 25 up here. And that's a pretty accurate graph. I don't know exactly where in between 1 and 2.5 the graph turns around. We don't know that. We won't know that until we go through calculus 1, precisely where this point is in here. But just turn it around somewhere in here, and then you have your sketch of your graph. Did we all get something like that? That's just it's a sketch. Okay, it's pretty accurate though, right? All right. One last problem here in your textbook, number 47. This is in section, what is this, 3.2? With these problems here, they give you a graph of a function, and they want you to determine the minimum degree of the polynomial. B, determine whether the leading coefficient is positive or negative based on the end behavior and whether the degree of the polynomial is odd or even. And C, approximate the real zeros of the function and determine if their multiplicities are even or odd. So I have a question for you, ladies. Number 47. What would be the minimum degree for this polynomial? What would be the minimum degree for this polynomial that has this graph?
3.
3. And one way you get 3 is the fact that it has 3 zeros. Do you agree? 3 x-intercepts, 3 zeros. Yeah, the minimum degree looks like 3. It's an odd degree polynomial. Would the leading coefficient be positive or negative based on the left and right end behaviors? Left behavior going down, right behavior going up. Leading coefficient would have to be positive or negative for an odd degree polynomial as such.
Positive.
Yeah, you're right. It'd have to be a positive leading coefficient. And we can approximate the zeros. -4 looks like a real 0, +1, and +3. And notice we do have 2 turning points, one that occurs at -2, 3, and another one that occurs at positive, it's hard to tell, +2, I don't know, -0.6 or something. So we do have 2 turning points here. And that would be the prediction based on the theorem here. Number 48, how many turning, what would be the degree of this polynomial, the minimum degree? It could be of larger degree, but what would have to be the minimum, the bare minimum degree of this thing?
4.
4th degree. You are correct. Look at the graph goes through this x-intercept, so these have to be of odd multiplicity, but the graph touches 3, does not cross through the x-axis at 3. So this would have to be of even multiplicity. So the bare minimum degree, you are correct. This would be a 1st degree, 2nd degree, bare minimum. That would give us a 4th degree polynomial bare minimum. And being an even degree polynomial, since the left and right behaviors have the graph going upwards, what would be the leading coefficient? Positive or negative?
Positive.
Positive. Yep, up and up is positive leading coefficient. And we have at most 4 minus 1, or at most 3 turning points. 1, 2, 3 turning points, as the theorem predicted. So, ladies and gentlemen, I hope you got something out of this section. We covered a lot. We looked at a lot of very powerful theorems in this section 3.2 here. And please do take the time to look at the other examples in this section. I think it's going to greatly enhance your understanding of what just happened here this morning. This is recorded, and I will post a link for this recording on Canvas as soon as I compile this video. It takes a little while to compile it. But if there are no other questions, I will let you